This short clip is a demonstration of Faraday's law of electromagnetic induction and of Lenz's law. The equipment consists of a coil of copper wire. It has a ferromagnetic core extending out from the centre of the coil. The coil is connected via a switch to a 240 volt 50 Hz AC supply. There are several aluminium rings of different thicknesses. First, a simple demonstration of Faraday's law. A light bulb is wired in series with a second coil of wire. When the current is switched on, the bulb lights up. What's the explanation of this behaviour? We know that a coil carrying a current will give rise to a magnetic field. And Faraday's law says that where there's a changing magnetic flux passing through a conducting loop or circuit, an EMF will be induced, causing a current to flow. And so the bulb lights up. In this demonstration, it might not be immediately obvious that the magnetic flux is changing. But remember, our coil is connected to an AC supply, so the current flowing through it is varying sinusoidally with a frequency of 50 Hz. And so the magnetic field that it produces also varies sinusoidally at the same frequency. Now, for a more dramatic demonstration of Faraday's law and the effects of Lenz's law. When the current is switched on, a magnetic field is produced that induces a current to flow in the aluminium ring. Like all currents, this induced current will produce a magnetic field of its own. Now, Lenz's law states that the direction of any magnetic induction effect is such as to oppose the change producing it. So the direction of this induced magnetic field must be in opposition to that from the coil. The ring experiences a repulsive force and is launched into the air. We can easily show that the force launching the ring into the air comes from an induced current flowing in the aluminium ring. This time there is a gap in the ring. It isn't a complete circuit, and so no current flows. Now, what would you expect to happen if we repeat the experiment with the original ring, but this time we cool the ring first? You should recall that when we cool a conductor, its resistance decreases. This means that the induced current that flows in the ring is much larger, and so the repulsive force experienced by the ring is also much larger. We've seen what happens when a ring is placed right on top of the coil and the supply is then switched on. What if we start with the current already flowing and then place a ring over the ferromagnetic core? The principles at work are just the same. The current induced in the ring due to Faraday's law produces a magnetic field that is in opposition to the field from the coil. The difference is that in the previous demonstration, the ring starts very close to the coil, and so the repulsive force experienced by the ring when the current is switched on is very large enough to launch it into the air. In this case, the ring hovers at an equilibrium point where the downwards force due to its mass is balanced by the upwards electromagnetic force. So what if we replace the ring with a thicker one, with a greater mass? Despite being significantly heavier, the thicker ring seems to levitate at roughly the same height as the thinner ring. The reason is once again related to the resistance of the ring. The greater cross-sectional area of the thicker ring gives it a lower resistance, and so the current induced in this ring is bigger. than the induced current in the thinner ring. So the increased weight is balanced by a larger electromagnetic force due to the larger current. The explanation of the jumping and levitating rings presented here is useful as an illustration and reminder of Faraday's law and Lenz's law. It should also remind you of a couple of key facts about resistance and about magnetic fields due to current-carrying coils. Actually, the explanation given here is somewhat simplified. If you're happy with the concepts explained here, you might want to think a bit more deeply about the following. Think carefully about the nature of the magnetic field produced by an alternating current. And think very carefully about Lenz's law. The levitating ring demonstration suggests that the magnetic fields are always repulsive. Is this actually what you'd expect? And, if not, how do you explain the levitation? And if you want something else to think about, watch this final demonstration and see if you can explain the behaviour of the thin aluminium foil ring.